Okay, well, welcome everybody to the next installment of the Dean's Invited Speaker Series, where we take this opportunity to feature friends of Yale who are kind of deep in the industry space to give our engineering community a sense that not only are we great at training you in educational opportunities, but we also have lots of ways for you to connect externally, and to hear what these folks are up to is really exciting, I think, for you and certainly for me. So today's speaker is our friend Jim O'Neill, who was class of, I believe, 1982 here at Yale. He's from Entegris, which is overseeing all technology there, and is a leader in providing essential ultra-pure materials to the semiconductor industry, and he plays an instrumental role in the chip-making process. So he's going to focus his talk on increasing a reliance on new materials to accelerate device performance and the difficulties associated with integrating these materials into advanced technologies. We've had a great conversation this morning about collaborative opportunities, and of course that's always takes a while to work out the details, but I'm extremely excited about this possible collaboration, and I look forward myself to hearing more about it. So welcome, Jim, and take it away.
Well, thanks, Jeff, and thanks for the opportunity to be here today. This is a bit of a homecoming for me. I did my undergraduate work here at Yale before any of you were born, but it's always good to come back and see what's going on campus and engage with you, the students. So the title of my talk is Materials Challenges in the Angstrom Era. I was trained as a chemist here at Yale and then went on and got my PhD at Columbia. I spent 23 years at IBM before joining Entegris. Entegris, I think, is the best kept secret in the semiconductor industry. We're the #1 supplier of advanced materials to companies that make chips, so TSMC, Samsung, Intel, but nobody's ever heard of Entegris. So part of my job here is to show you how fascinating the materials industry is, how critical it is to the advancement of semiconductors, and hopefully you'll walk away with an impression of what we do and why it's so important. I mentioned the Angstrom Era because semiconductor devices are advancing through a process of miniaturization, and we have now converged on a regime where device dimensions are measured in atomic diameters, and the challenge of engineering precision, pure materials at atomic scale dimensions is not easy. I'll give you a little bit of background about the semiconductor industry and some of the factors that are driving the industry. I start off with volume because the semiconductor industry is growing, and the outlook is that it will continue to grow for the foreseeable future. From the time you get up in the morning until you go to bed, many, if not most, of the things that you come in contact contain semiconductors, whether it's your watch, your phone, your laptop, your television, your car, your refrigerator. All of these contain semiconductor devices of various levels of maturity. And if you didn't think semiconductors were important, just remember back to the pandemic, where it became hard to get access to your favorite consumer products because the semiconductor supply chain had been disrupted during that period. So semiconductors are here to stay, and they're becoming instrumental. The industry is forecast to grow to about $1 trillion by 2030, 2032. That is nearly a doubling in the size of the industry. That means the industry is going to build more fabs, it's going to run more wafers, and on those wafers it's going to apply more materials. So this is an industry that is going to be dragged along, if nothing else, by the expansion of semiconductors. Obviously, the next big factor driving the industry today is AI. An AI engine basically is represented by this cartoon here, and it will contain an advanced logic processor, a GPU, probably designed by NVIDIA, most likely manufactured by TSMC. It's coupled with a stack of what we call HBM DRAM. This is high performance, high density, high bandwidth memory that contains all the data that the GPU is going to process. And it's coupled together on an advanced packaging substrate. So in this one embodiment, we've packed an awful lot of memory and logic processing horsepower, and we're driving 3 roadmaps at the same time: advanced logic, advanced memory, and advanced packaging. So this is single-handedly driving the industry. The rest of the industry is actually in a little bit of a doldrums right now given the overall market conditions, but AI continues to grow. Next is complexity. The complexity of applications into which semiconductors go is ever increasing. I've got a picture here of Apple's Vision Pro, which is kind of old technology at this point, and it only came out a couple of years ago. What I'm actually more interested in is some work that I saw. I visited Google's Google Labs out in Mountain View a couple of months ago, and I got a chance to talk to the team that's driving what they call Project Astra. Now, Project Astra is a personal assistant resident on your cell phone, voice activated and visually enabled. So you can walk around with your cell phone, camera on, and interact with your environment. And it's absolutely amazing. There's a YouTube video where Google has sort of portrayed some of the capabilities, and you should look it up and watch it because it's really very impressive. The next thing I'll highlight is reliability. Reliability didn't always used to be a driving force within the semiconductor industry. And that's because a number of years ago, technology didn't have to last longer than 3 years because by that point, your technology was obsolete and you just put new chips, you buy a new device with new chips in it. However, today, semiconductors are going into life-critical applications like self-driving vehicles, autonomous functions, and you can't be driving down the interstate at 60 miles an hour and have a reliability fail with your automation chips. So reliability is becoming a serious driver for device requirements in the industry. I'm sure you're all aware that the industry has advanced consistent with an observation that was made by Gordon Moore from Intel. It's called Moore's Law. It basically says that cost performance or memory density or any parameter that's of importance to the semiconductor industry will effectively double every 2 years. And historically, this was achieved through miniaturization, which was accomplished through optical lithography techniques. You use light to project circuit patterns onto a device, and improvements in optical lithography enabled you to continue to miniaturize, and that allowed you to get better performance. Until what we call the 28 or 20 nanometer node, when performance benefits as you shrunk didn't pan out as consistently. So at that point, the industry needed to adopt alternative paradigms, other innovations, such as new devices and new device architectures, the materials that go along with them, connectivity improvements, which includes advanced packaging. And I highlight quantum compute here. It's a little out of not consistent with the rest of the trend. But quantum compute, I think, is still a little bit off in the future, but it will ultimately be adopted for mission-critical accelerator-type applications that can't be done with any other form of computing in a reasonable lifetime. And I highlight it here because Yale is one of the leaders in the world for developing quantum compute technology. The industry roadmap is highlighted. Borrowed this chart from TSMC, and I show the roadmap on two levels. So TSMC is the world's foremost producer of advanced semiconductor devices. Roughly 95% of the world's most advanced semiconductors are made in Taiwan by TSMC. We can argue about the geopolitical instabilities that leads to, but suffice it to say they are the industry experts at this point, and they have a roadmap for monolithic silicon integration, or the ability to produce chips up to, including more than 100 billion transistors. They manufacture NVIDIA's latest AI chip. It's called Blackwell. That chip has 208 billion transistors on a piece of silicon a little bit larger than the size of your thumbnail. So these are really small. This is very complex processing. But that's not where they want to end up. They want to basically be able to create packages, advanced packages, with 1 trillion transistors. And they're going to do this, they're going to enable this by 3D silicon stacking, basically taking these monolithic devices, stacking the active layers on top of each other, and then using advanced packaging technologies, put together package systems that would basically contain 1 trillion transistors. And this is going to pose all sorts of problems for inspection and testing, but the roadmap is there, and TSMC is bound and determined to achieve it. And by the way, they're increasingly looking to invest in countries outside of Taiwan. So they've stated plans to invest about $165 billion in the US to build 3 new fabs, 2 packaging facilities, and an R&D center here in the United States. So this is, I think, a good sign for sort of helping rejuvenate the US semiconductor industry. In order to keep pace with the roadmap, we need new technology innovations, and these span the various paradigms that I talked about before. The state of the art in optical lithography is accomplished with what we call extreme ultraviolet patterning, EUV lithography. This leverages light with a wavelength of 13.5 nanometers to create circuit patterns down below 5 nanometers in width. Devices are now being integrated into the vertical dimension. Flash NAND has gone from a planar device now to the method for increasing node density is by stacking layers on top of each other, sort of like creating a parking garage with multi-stories. You can park more cars in a taller garage. Same concept conceptually with 3D NAND. If you look at the individual transistor level, all the schematics you see in introductory EE handbooks show a semiconductor device which is planar. You've got source, drain, and a gate in the middle. Devices these days are three-dimensional. They transition from planar devices to a FinFET device, which basically looks like a fence, or a gate-all-around device, which looks like a series of stacked garden hoses on top of each other. And through very careful materials engineering, they're able to create the ability to switch current through these gate-all-around channels very effectively. One of the big space hogs for a chip is the circuitry required to deliver power to the 208 billion transistors on the chip. In fact, the power distribution circuitry can take up more space than the active circuitry itself. So there's work going on right now to move that to the backside of the wafer and to drill very deep holes through the wafer to connect to the devices from the backside. I had an opportunity to talk at Rajiv's class yesterday about advanced packaging and 3D IC. This actually is the future of continued density improvements. That's how TSMC wants to get to 1 trillion transistors on a device. This introduces a whole new set of challenges, not the least of which is how do you dissipate all the heat that's generated by all the active layers that you've stacked on top of each other. But suffice it to say that a ton of innovation is required, and all of this innovation can't be done without innovation in the materials space. There are new materials and new improvements in performance characteristics of the materials that are required in order to achieve each of these innovations. And frankly, this isn't new. If you look at each of the individual technology nodes and sort of stack up all of the new materials that were required to achieve each of those nodes, the list gets tall very quickly. So today, we're sort of in this regime here where you need new materials, say, for example, to create the conductive channel. There are new materials that, if you look at the roadmap, there will be 2 new device architectures introduced by 2030, and each of those will be enabled by new materials that are required to actually engineer the structures that are envisioned by those devices. And then once you've created a chip with 200 billion transistors on it, you need to be able to wire it all up. So you need to make contact to the transistors, and you need to be able to wire from one transistor to another to get the functionality you need. And this is going to drive the need for other new materials, including new metallurgies that conduct electricity better than today's state of the art. And I'm going to go into some detail there. And then I also mentioned the new materials associated with packaging. I'm going to just touch 1 minute on sort of the future of devices. There's a colleague that I used to work with at IBM. His name is Philip Wong. He's now the professor of EE at Stanford. And I asked him, what are transistors going to look like in 10 years? And his view is that you're not going to have a standard silicon transistor where you simply adjust the VT to get low current, high power, whatever. You're going to need domain-specific transistors, and these are going to be predicated on different kinds of materials. So if you look at his cartoon or of his vision, you're going to have a base layer of standard silicon devices. But if you need low ion IF devices, maybe you're going to create an array of oxide-based semiconductor FETs, things like indium gallium zirconium oxide, or ITO or IWO. And these are fundamentally different from silicon-based devices and are predicated on a whole new material set. If you want to go farther up the stack, maybe there's going to be a layer that's just 2D materials, and these would be molysulfide, molyselenide, materials that create conductive layers that are in geometry, have preferential conduction in the planar direction. We're doing some work today with the University of Illinois at Urbana-Champaign to investigate how to control the phase of these materials so that you can create semi-metal and semiconductor regions so that you can actually make contact to these films to inject current into them. And then at the highest level, the thought process is that you could have something like a carbon nanotube FET, which would be very high on, very low power, very high performance devices. So you begin to get an array of devices that fulfill specific applications, are lower power than what we have today, and all are predicated on the implementation of new materials. By the way, the level of difficulty of integrating these goes up as you kind of go up the stack here. We can do metal oxide FETs. I think we're pretty close to being able to demonstrate 2D FETs. I think carbon nanotubes remains to be demonstrated. I'm going to jump around a little bit here. I talked about 3D IC. The big unsolved problem there is heat dissipation. I always feel legitimized. 2 days ago, I picked up the New York Times, and there was this article which basically talks about diamond as a heat spreader within the semiconductor industry, and I always feel validated when I can get my science legitimized by the New York Times. But suffice it to say, you never used to be able to find relevant problems to the semiconductor industry in the popular press, but these are really important problems that are even acknowledged by the non-technical community. So I want to talk a little bit about some of the challenges of implementing new materials. I think universities, industry labs do a really good idea saying, well, you know, why do we predicate everything on silicon devices, and why do we wire it all together with copper? There's all these other materials out there that would be better. The answer is it's really hard to make these materials, to integrate these materials into a working structure that yields and can be built at a cost-competitive manner, which is really where the rubber meets the road in technical industry, is you actually have to take a good idea, manufacture it in volume, at yield, at a cost that somebody's actually going to buy, like your cell phone. So today, if you created a chip, 200 billion transistors on it, you need to be able to wire all those transistors together. So 208 billion transistors means that your initial levels of wiring are going to be very small, probably smaller than 10 nanometers. Historically, devices in a semiconductor device were wired with copper technology. It's a good conductor. It's just like your home electrical conductions. But when you decrease the width of the conductive wiring, the resistivity of copper, shown in red, increases dramatically, and copper becomes more of a resistor than a capacitor. So you're going to need a new metallurgy. There's a lot of candidate materials out there, some of which are unattainable, some of which are unaffordable. But two which are very promising are molybdenum and ruthenium. The industry is working on both of these. Both show better resistivity at low dimensions. And molybdenum is being examined as the first candidate because the sense is that it's more of a drop-in for the way in which copper, or in this case also this applies to tungsten connections, are made. And so molybdenum activity is very widely underway. Ruthenium actually has better electrical extendability, but it's more difficult to integrate. The scheme by which ruthenium would be applied to a wafer is very different from that from molybdenum. So I think we're going to see kind of a progression of molybdenum first and ruthenium to follow. And molybdenum and the benefits of molybdenum have already been demonstrated in 3D NAND structures. So I mentioned before the way to increase density in stacked 3D NAND is to increase the number of layers. However, you need to be able to make contact with all of the individual storage nodes in this stack of memory. And the way in which that's typically done is you drill a very deep hole, you fill it with a conductor, and that becomes the word line for your device. Historically, that conductor was tungsten. But as this stack gets taller and taller, tungsten becomes too resistive and no longer works. So molybdenum was offered as the alternative. It's been integrated by a number of memory manufacturers and demonstrated already about a 30% benefit in overall line resistivity, which is huge. That said, the process of introducing molybdenum into a build like this isn't so simple as just taking out the tungsten and putting in the molybdenum. I'm going to go into a little bit of detail with respect to that. So first of all, molybdenum comes, if you want to apply molybdenum to a wafer, you need to be able to get the material into a process chamber where it can be then dissociated from its precursor and deposited on the wafer. The way in which molybdenum is applied today is through a plasma-enhanced chemical vapor deposition process. You flow gas into a process chamber, apply a plasma, the molecule falls apart, the molybdenum falls on the surface, and you end up with a deposited film. The challenge is that the precursors for molybdenum today are solid materials. It's difficult to generate a gas from a solid, so you need to develop a capability to sublime the solid molybdenum precursor into a stable gas, deliver it to the chamber as a gas without it condensing all over the place so that it can be applied to the surface. So this is very different from traditional deposition processes, which are typically delivered either as, where the precursors are either gas or they're vapors generated from a liquid. Some liquids have vapor pressure, it's easy to get the gas off. So we've developed and had to develop a very carefully engineered delivery vessel, which is basically a thermal system engineered to hold the molybdenum precursor in a way that allows for efficient utilization of the material, stable process flow. These molybdenum precursors are chlorine-based. They're very corrosive. The systems are made of steel. They corrode. So we've engineered special coatings for these systems. We've engineered special filtration to ensure that we are able to reduce any form of defectivity. The point is, it's not an easy thing to just change from tungsten to molybdenum. You need to worry about how you're actually going to deliver to the gas to the chamber. And so this is sort of problem number one. However, solid precursors are seeing more prevalence in the industry given the critical nature of a number of applications. Today's gate dielectric is a hafnium oxide-based material. It's generated from hafnium chloride, a solid. There are aluminum oxide films used in 3D NAND applications. They're generated from aluminum chloride. That's a solid, and it goes down the list. So solids is problem number one. Problem number two is that molybdenum is not tungsten. It's a different metal. It has a different electrochemistry. So not only do you need to worry about how are you going to fill a structure by depositing molybdenum into it, but what is that molybdenum then going to see in the subsequent process steps? So if you start with a feature at the very left-hand side of the page here that you need to fill, you need to figure out what's the process conditions you're going to use. What precursor are you going to select? What kind of tool conditions are you going to run it at? Those decisions are going to affect the nature of the film that you get. Its grain structure, its smoothness, its porosity, and all of those characteristics. After you've filled the feature, you need to remove the excess material from the top of the feature, and that's done through a polishing process. Well, the polish process is going to depend on the characteristics of the film that you just deposited. So you're probably going to have to adjust the slurry formulation, the polished slurry formulation, to accomplish that kind of fill. If you change the slurry formulation, now you need to consider how you're going to clean up all the debris that you left behind on the wafer, so you're going to need a new clean formulation. And very quickly you see this cascading event. You just want to put molybdenum in the structure, but everything else downstream changes. And that takes time, that affects yield, and that's really what the semiconductor process engineer is trying to do in the fab, is to try to figure out how to string this together, not just for one level and one material, but all the materials that are used across 2,000 steps in the process lab. Just indicate that each step you do has a subsequent ripple effect downstream. So it's not just about the characteristics of the material that you want to implement. It's about all of the downstream effects. And I put this picture up because I think laboratories in universities and in industry do a really good job characterizing the nature of materials that would be ideal candidates for implementation in new and advanced devices. Those materials are then delivered to the fab where the poor process engineer has to figure out how to make it work. And just to give you an idea of what the workload is on those process engineers, today's logic processing sequence has as many as 2,000 steps, and that number is increasing as technology gets more complex. the time between technology node qualifications isn't changing all that much, so the unit process engineer is having to do more in a shorter period of time. So what's missing in this is not just characterization of the material properties, but a characterization of what are the likely interactions that that material is going to have when it comes in contact with other films in the stack, when it comes out in contact with other liquids that are used to clean or polish the solution. If we had, and a lot of that can be done in the laboratory on the bench, doesn't have to be done in expensive process equipment, but if we had better insight into that, the process of the unit process engineer in the fab would become much easier. And the name of the game in today's semiconductor industry is speed to yield. The company that can get to yield fastest is going to make all the profit. So all of the focus on the semiconductor, on today's semiconductor fab is on how are we going to yield this technology, and the industry basically needs help, and I think that's one area that could benefit. So overall, the industry is facing the challenge of a whole host of new materials being implemented on very complex geometries, often at atomic scale dimensions, and I'm going to argue at zero defectivity, ultra high purity, all at the same time. So this is not an easy problem to solve. It's not really just about the material itself. It's about how you make this material work and yield on a wafer. So the challenge is complicated even more from there. Today's chips, monolithic chips, are typically designed with more and more functionality. You want to put more processing cores in. You want to put more flash memory in. You want to put more embedded DRAM in. What that does is that it increases the size of the die of the chip that you're trying to manufacture. Larger chips, so chips are made on a semiconductor wafer, and larger chips take up more real estate. So for the same defect density on a wafer, larger chips are going to yield much worse than smaller chips. So today's NVIDIA chip, AI-based GPU is about 800 square millimeters. There's 64 die per wafer. Apple's typical cell phone die is about 100 square millimeters, so there's a lot more die. So TSMC can yield Apple die much better than they can yield NVIDIA die. So this whole transition to larger die causes a problem, causes a big challenge. The other thing is that as technology advances, the size of defects which will kill your chip decreases. And in fact, it decreases faster than improvements in defect inspection capabilities that the fab uses to see it. So effectively, our semiconductor manufacturers are operating in the dark. They can't see all the defects that are killing their devices. So this is not a really good place to be in. That is also combined with the fact that purity specifications for some types of impurities are now spec'd down to the part per quadrillion level. This is effectively, in my mind, almost meaningless because it's not characterizable. But just part per quadrillion is equivalent to about the volume of a drop of water over Niagara Falls in a day. I mean, you can't detect at that levels. So the challenge of achieving yield on a time scale that's needed for new node introductions is enormous. And so we, as a material suppliers, our customers are telling us, look, we want the purest materials you can get, but that's not enough. We need a complete solution that includes the filters, the packaging, the sensing and control, the wafer environment, in order to ensure that we're actually going to be able to achieve yield when we implement these new materials. And this is a very valuable proposition. A 1% improvement in yield for an advanced logic fab is worth about $500 million a year in profits. It's worth about $150 million a year for a memory fab. So this is why all the focus is on speed to yield. 1 point of yield is worth more than all of the materials that were used to make the die in the fab. And just to kind of reiterate the sort of halo effect, going back to the implementation of molybdenum in 3D NAND, the taller 3D NAND structure requires a more conductive material, that's molybdenum. That drives new clean formulations because the electrochemistry is different. The new formulation requires new filters. And so very quickly you see that what started off as a deposition precursor exercise now has this halo of other capabilities, this holistic problem set which needs to be addressed all at the same time because that's what the fab is trying to achieve. So just to get an appreciation for material science is critical to achieve the performance characteristics, but a holistic view of how materials behave in complex environments is really where the rubber meets the road here. A couple of other factors that are critical in the semiconductor industry are variability. This goes along with defectivity. If your process can't be controlled to within a very tight tolerance spec, you're not going to be able to ship all your parts characterized as performing in a certain way. So increasingly, the industry is relying on chemistry to control the reaction, control the process that's being required. So I call this the self-something era. And for example, if you want to create very dense features in a regime where it's difficult to control the patterning variability, you just create a pattern that you can control, and then use chemistry to grow films on the sidewall of these patterns, remove the original pattern, and now you've got pitch doubling. That was done by chemistry. You didn't do that through lithography. The most advanced devices today are called gate-all-around devices. These devices are about 10 nanometers across, 5 nanometers tall. You have to engineer precision gate films that control these devices down to atomic scale dimensions on surfaces that you can't even see from the top of the wafer. So how, first of all, are you going to deposit films on them? And second of all, how are you going to characterize them? It's a difficult problem. So one way in which this is approached is through self-limiting processes, things like atomic layer deposition or atomic layer etch, or area-specific deposition, which is illustrated here. In this case, we're trying to deposit ruthenium on the top of a tungsten contact. We don't want to use lithography to pattern it. We only want to use a chemical process which will deposit ruthenium only on tungsten but doesn't deposit on dielectric, and that's the kind of scheme that's being leveraged today. So these self-something processes enable extreme levels of conformality and selectivity that's required to control the variability of devices. The other challenge that you've got to face is that you're dealing at atomic scale dimensions. I borrowed a chart from Tokyo Electron. It's a manufacturer of advanced process equipment for the semiconductor industry. And they plotted for various technology nodes kind of a visual of gate dimensions versus metallization line widths, not as a function of nanometers, but as a function of atomic diameters. So you can see already by the 5 nanometer node, we're talking about features that are on the order of tens of atoms across. So this is difficult to characterize and difficult to engineer. And you even need to consider these atomic scale effects with wet processes, liquid formulations that are applied to wafers, for example, for selective etching or for cleaning applications. We did some modeling work looking at how does a clean formulation that you mix up in the lab, how does that behave in a nano-confined space, like a small via or a line that you're trying to pattern or clean, where the dimension of the line is on the order of the diffusion lengths of different components in the formulation. So if this was your original composition of additives in a formulation, when you apply this to the wafer, our models tell us that the formulation is going to change dramatically in the very feature that you want this formulation to work. And so you need to understand that if you're going to get these processes to work. And so we're kind of beginning to leverage digital technology to help us understand that. I'm going to try to go a little bit quick here because I think we're probably running a little bit late on time. But I mentioned before that today's state-of-the-art patterning is accomplished with extreme ultraviolet lithography. EUV lithography runs on a photon with a wavelength of 13.5 nanometers. This is a photon that has about 20 times the energy of the previous generation technology. It runs at, so previous generation technology was a 6.4 EV photon. EUV photon's greater than 80 EV. What this means is that for a given dose, lithography is applied through flashes of light, and that dose, for the same dose, you have many fewer photons for an EUV, for EUV application. What this means is that stochastics now come into play. The absorption of a photon is a probabilistic event, and fewer photons means that there's an increased probability that some of those photons aren't going to hit where you want, and so you're going to end up with poorer patterns just due to stochastic effects. So a material solution to this is that you would want to come up with a photoresist that has a much higher absorption propensity for EUV photons. This has driven us to a new regime of photoresists that contain metal oxides. In this particular case, it's tin, but typically you do not want to put metals in any chemistries that come in contact with devices, and yet you need to do that here. So this is a material solution to a stochastic problem posed by photon energy dependence in the most advanced lithography out there. So there's a ton of problems that need to be solved in the material space, which means that there's a whole portfolio of challenges that our innovators are facing today, and they can't do the job the way they used to. They can't go in the lab and mix up chemistries and try it out on a piece of process equipment. It takes too long, costs too much, so we need to use new tools. And so I think there's a trend across the industry to leverage digital tools, modeling and simulation at different scales, to be able to better predict where you should look when you start an investigation. So this is just a portfolio of capabilities we've been using in-house, including first principles for computational chemistry, all the way down to coarse grain models and multi-physics models to sort of characterize the space in which we're operating in. And we use this for two primary purposes. One is, how do you down select a wide portfolio of viable chemistries to those which you can now direct your laboratory workers to go in and experiment on. So maybe there's 50 candidates and you want to just have them concentrate on the 5 most promising. Well, we arrive at that through computational chemistry techniques. Secondly, we use this to get mechanistic understanding of how a process that we're developing might work, because if we need to make adjustments, we need to know where to turn. And I'll give you a quick example of that. We were developing a formulation that was intended to provide a selective etch of one material in the presence of another. This process generated a byproduct which became suspended in solution and then would redeposit on the surface and kill the reaction. So we said, okay, this isn't working, we need to take a new approach. So the two pathways would be, well, okay, we can getter all the stuff that's in the formulation and take it out of commission, or we can inhibit the sites on the surface of the wafer to prevent the material from reabsorbing and not kill. Either way, you kill the reaction. You extend the ability to continue the reaction. So we built models pursuing each path, and then compared it with some of our empirical studies. And what we found very quickly was that the surface inhibition mechanism was the one that agreed more with our laboratory observations and allowed us very quickly to turn to developing new inhibitors for the surface and dramatically shorten the amount of time that we were able to come up with a solution for our customer. We came up with what we thought was going to be the best solution. We shipped it to the customer. They said, yeah, this worked for about 5 minutes, and now we need you to reinvent it. And we're like, okay, they need this solution next week, and we don't know where to turn. So we quickly put this in place, and we didn't get them a solution next week, but we were able to get a good solution within a couple of months. In any event, just a really quick snapshot of some of the challenges that the industry is facing in the materials space. They are both fundamental and fascinating in nature. But just to summarize, as we enter the Angstrom Era, more performance improvement of devices is going to come from the materials that are implemented than from the architectures and the way in which the devices are engineered. But engineering new films on challenging geometries at atomic scale dimensions with ultra-high levels of purity and zero defectivity all at the same time is not an easy process. So the successful integration of any material is really going to require an understanding of that whole ecosystem and the ability to provide a more comprehensive, holistic solution to the problem we're trying to solve. And the problem set is so large that we're having to rely increasingly on digital techniques to help us predict where we want to go, rather than trying to arrive all through analytical studies. So that's the meat of this talk. I do have a couple more charts, if I can just borrow 2 more seconds, and this is more of a challenge. There's no answers here. It's just a challenge. I figure if I have an opportunity to influence young minds, it's this problem here. Semiconductors and sustainability is a huge challenge. Give my little political digression here. I mentioned that the industry is advancing at the rate of Moore's law, and there's a New York Times columnist by the name of Thomas Friedman. A number of years ago, he wrote a book called Thank You for Being Late, and it describes 4 or 5 megatrends that are evolving faster than society's ability to adapt to them. So one of those megatrends was Moore's law, and he highlighted the digital divide, inequitable distribution of access to digital capabilities, workforce displacement. all plausible. If you read the book and agree with his premise, and then you listen to NVIDIA's CEO who says, well, AI chips required for AI are advancing 10 times faster than Moore's law. You thought the problem was bad here. We're going to have a bigger problem as we move forward. I only mention this not because I want to communicate any political bias, but I do want to provide some thought about context. We as innovators develop technology. There's a context into which technology fits, and we should at least acknowledge it. So that's one of the things I wanted to get across there. And two very specific things is AI and power consumption. Power consumption by data centers was already going through the roof. It's stressing grids in places like Virginia and Tennessee. AI is contributing significantly to that, to the extent that Microsoft is planning on opening Reactor 2 at 3 Mile Island. 3 Mile Island, for those, you guys weren't around when 3 Mile Island's almost melted down. But 3 Mile Island was a nuclear reactor in Pennsylvania that was a near meltdown. It's been shut down for decades. And the fact that we need so much power to run a data center that Microsoft is willing to investigate reopening it is a real statement. Problems worthy of innovation in this regime are if you're consuming so much power, a lot of it's going to come out in heat. We need to worry about heat dissipation materials. And if it's consuming so much power, maybe we should make devices that consume less power. No answers, those are challenges. The other thing, I mentioned the industry is going to grow. It's going to achieve $1 trillion. This means more wafers, more materials. Materials used in the semiconductors include PFAS. In many instances, these are in essential uses, photolithography, plasma etching. There's no way out, but PFAS is a 4-letter word. This is an area that needs innovation as well. Enough said. Thanks for your time.
Thank you very much for that inspiring talk. So I have a couple of questions, and then I'd love to get questions from all of you. So first of all, I feel like this talk really, it's all of this. You're not talking about even just materials is, of course, the headline, but you're doing chemistry, you're doing design, you're doing computational modeling. It's sort of the whole spectrum of engineering is sort of encapsulated in the problems that you're articulating. What is, as you state these kind of fundamental problems, is there kind of a particular track or direction through an undergraduate or other engineering educational experience that you think positions our students best for this work?
Yeah. If I look at the most successful teams that I've worked with in industry, whether it's been at IBM or at Entegris, increasingly, and particularly in the semiconductor space, these are problems accomplished by domain experts in multidisciplinary fields. So each team would have a chemist, it would have a physicist, it would have a chemie, it would have a data scientist. And it's really that combination of skills that enables the problem to be solved. And each problem is a different problem, requiring a sort of a reselection of the folks that you want for the team. So I would say there's a variety of fields, specific areas, domain expertises, or areas of discipline that are relevant and important here. One that I think is emerging is, I was talking with the CEO of a company called Athenia, and they do a lot of quantitative machine learning, AI processing, and the woman said that the most valuable skill is a domain expert with digital capabilities, somebody who can combine AI or machine learning or modeling and simulation with their domain expertise to sort of get a jump start and accelerate the thought process. But this is a multidisciplinary field that requires skills across scientific and engineering disciplines to get the job done.
That's fascinating. So, that was sort of the next question I was going to ask, is you sort of mentioned both the need for simulation and modeling to get at these problems sort of in advance of the laboratory experiments, but also, how the process by which that leads to new mechanistic understanding and new physics, chemical models for phenomena. is there kind of an interplay there? We wrestle with this a lot as we build up, both efforts in data science and more data-driven investigation relative to more traditional numerical simulation or numerical analysis methods. And I sort of would imagine it's the same kind of interplay that you're describing there, that you need both.
Yeah, I mean, which comes first, the data or the experiment that generates? Right. It's more of a cycle, I would say. There was a question yesterday from the talk that I gave about sort of if you're considering something like 3D IC, where you're 3D integrated circuitry, where you are stacking layers of circuitry together, sort of you're creating a problem of dumping a lot of power into a small volume. You need to dissipate heat, or you need to reduce the amount of power that the amount of demand on the power. What's the optimal configuration? And how do you determine that? So you can either build it all up in many different ways and look at it, or you can simulate the heat flow, simulate the power consumption, look at the distribution across sort of a cube space. And that's an area that's wide open. It's just, we don't know. We're discovering this as we go. So, folks who can think about problems in that context, who can bring new tools to look at what are the boundary conditions about how we think about this? I said larger chips are a problem. Do you want to go all smaller? How small is too small? If you go too small, now you have to stack higher. Well, that's going to give you a yield problem. So there is an optimal space here, but we don't know what that is. And I think we need tools and more intelligence to figure that kind of thing out.
All right, I could go on, but maybe, are there other questions from the audience? Yeah, go ahead.
Hi, let's talk, Jim. So I had a question, you mentioned when we invented or create a methodology for depositing a material, but then it's very hard for the engineer in the industry to figure out what the downstream process should be, right? So I'm wondering how you look at the miscommunication issue between the academia and the industry. I think that's a long-lasting issue. Oh,
this is a very long philosophical question. I think that there needs to be, so the longer answer to this, I would say that the industry and academia used to do a better job of this. There historically was better overlap. If I go back all the way to the 1990s, I actually was in it before that. I would say that if you look at the research and development curve, the amount of energy or money or whatever that you put in gets you pretty far early on, and then you got to put a lot of money or energy in to sort of get to the point where you're ready to launch into manufacturing. I would say historically universities did a really good job on the R part and maybe even into the beginning of D. And industry did a really good job, certainly with manufacturing, piloting, developing, and even reaching back into late stage R. So I'm thinking IBM, Bell Labs. There was a big overlap between industry and academia at that point. I think because of complexity in the industry and the cost of doing that work, universities have pulled back into fundamental R, industry has pulled back into qualification of products, and there's this big gap in the middle. I think we need to rebuild that gap. I think it's been filled opportunistically with entrepreneurism, startups, which have very different motivations. We're in a different environment. I think we need to look for opportunities to improve that communication and improve that connection. I think today, without any further change even in the academic approach, things like modeling, simulation, analytical techniques, methods to characterize things are starting points today where we can feed directly from university into industry, and that starts the conversation. And then hopefully maybe we can target specific projects where there's much closer linkage of students or faculty to industry experts and needs, and I think that's what we're exploring or have been for some time now. Long answer to your simple question.
It's a hard one. Any other? Yeah, Abby?
Yeah, so I'm curious about the upstream sourcing of some of the materials that you mentioned. So we're hearing a lot from the federal government about critical minerals and so on. So I'm wondering, something like that molybdenum chloride salt that you showed, where does that come from? Do you dig that out of the ground? Is it mined? And what are the challenges that you all face?
So molybdenum actually is not a problem, and there's a huge molybdenum mine in Colorado. called pyramid molybdenum. So molybdenum is not an issue, but there are other materials that we utilize that are quite problematic. Yttrium is one, gallium is another. The government's done a good job identifying critical materials. Many of them come from China and have some restrictions on them today. Many of them come from Russia, and that supply chain is a little problematic. Fortunately for a company like Entegris, we deal at the far end where we'll take semi-pure stuff and turn it into ultra-pure stuff, so we don't worry about the mining or the original sourcing unless the source goes away. And that has happened for some of our stuff. So yeah, this is a problem. I think a more open, more stable geopolitical situation would help global manufacturing in general. That's a problem.
Where is it? Next question. Yeah, go ahead.
Mine was a little similar to the first question. I guess I was interested in that gap you mentioned about base R&D. It seems like maybe TSMC is doing a good job about that, potentially. How are other companies not doing such a good job with that implementation of new materials?
So TSMC can afford brute horsepower, and they throw a lot of resource pretty much at everything. I don't know that they necessarily, so they do sponsor a lot of university research. They also have a very big R&D and pathfinding endeavor. So they've kind of brought in a lot of they've moved down the R chain from just development and partnering. It didn't always used to be the case. They were originally a pure foundry. They would just make designs for fabless companies, and they would do enough research to be able to get a process and a PDK, a process design kit, to the customer. I think today, because of the challenges and the fact that they're now leading the industry, they need to bear the brunt of the R that goes along with the leadership position. I think they face the same challenges that all companies do, but they just they have the wherewithal to throw more money at it. Intel used to do this. Intel has the problem that they missed a couple of technology nodes, and that's catastrophic and hard to recover from. So we're all very hopeful that Intel can pull out of the trough, and I'm sure that they'll find a space, but they've fallen kind of far behind at this point.
Yeah, back here.
My question was, that last graph that you showed, it looks like there's a lot of almost like unlimited room for growth in this space for like the semiconductors. Does the Earth actually have enough, supply of these rare earth materials for this growth that we perceive?
Well, that's a multifaceted. I can give you a multifaceted answer. Many of these materials are used at very, very low volumes. So, we're talking about engineering things at atomic scale dimension. We're talking about really, really thin films, not a lot of material. So it's more digital. Can I get access to the material, or can't I? I'll give you a more interesting answer, though. So Micron sort of extrapolated the amount of data that we produce, that the world produces. So in 2025, I think the number is 181 zettabytes of data. And they assumed that you need to store some fraction of that to process it, look at it, whatever. And then if they extrapolated the growth trend into the future, they quickly found out that there wasn't enough silicon, there wasn't enough sand on the beach to make that many silicon wafers. So it's a long way out, but they wanted to argue we need a paradigm shift. So they actually started working with the Harvard Department of Genetics and sort of pioneered DNA as data storage, which is a really, really cool concept. It sort of combines life sciences with semiconductors, and there's a company in Boston called Catalog. I'm absolutely personally fascinated by this company. They were able to create a scheme where they could generate what they call DNA restriction fragments, short segments of DNA, each of which represent a word or a concept. And then they were able to string it together in a way that they could write Wikipedia, all of Wikipedia, in a milliliter of DNA containing fluid. And then if they wanted to this is for archival storage because writing DNA is not like reading and writing DRAM. I mean, it takes a really long time. But if you extrapolate the improvement in the ability to read and write DNA, we've come down 4 orders of magnitude in the last 20 years. We're only 3 orders of magnitude off, so wait 20 years and maybe we'll be there. But for archival storage reasons, it's kind of already been demonstrated at least once. Kind of an interesting concept to think about. Yeah, and I've actually toured their facility. It's just a really, it's kind of mind-blowing what they're able to do, and that comes from a basic extrapolation that maybe someday there's not going to be enough silicon to make wafers. So,
You know what that date is?
where that date is?
Or like what year that was that they estimated?
I think it was like I'm kind of guessing here, somewhere between 2030 and 2050. I can look it up. We can.
It's not that far away.
No, it's not. It's not that far away. Not more on the 2050 side, but there's a great video on YouTube that you can look. It's sort of this company's catalog hype video. They also have this concept that if you put all this information in DNA and it's in a liquid and can design a reaction process, you can do massive parallel processing through certain additives to basically instantaneously process from one state of data to another state of data and perhaps back. So still a little bit conceptual, but people are thinking about where to go with this, and it's really, I just find it absolutely fascinating.
All right. Maybe we can end on that aura of fascination and send you out into the world to carry it forward. So thanks again, Jim, for coming.